Hello everyone, this is the fifth class. What we are going to do today is to study a technique called regression, right? So today we are going to talk about simple regression in which we have only one independent variable. And then next time we are going to talk about multiple regression where we have more than one independent variable, right? Now, so what is the regression? The simplest way to describe what the regression is to say that regression analysis is a technique which is used to find a relationship between independent variable and dependent variable, right? Just like linear equation, suppose you have dependent variable y and independent variable x. Finding a relationship means what? You find the equation like this, right? In terms of this equation, finding relationship means you want to find the intercept and also the slope, right? Now, there are two purposes for using regression, right? One is to predict something, and second purpose is to find whether the relationship is positive or negative. Suppose we have equation like this, right? Predicting means that if you plug some number here for x, and you can find the y values, right? Now the second purpose is to find whether the relationship is positive or negative, right? In this case, you look at the coefficients here, right? Since we have a plus 3 here, so you can say that there is a positive relationship between x and y, right? So these are the two purposes for using regression. And we are going to use this example for today's class. In this case, we have average hourly temperature as an independent variable, and we have a weekly fuel consumption for dependent variable, right? So we are going to try to find the relationship between these two. So we are going to find the intercept and the slope of this equation, right? Now I'm going to explain basic principles for regression, right? Now let's go to a note. So let me explain the basic principles of regression, right? Remember that in statistics, right, we are interested in finding something about population, right? Suppose we have a population here, okay? And then there is an independent variable and then dependent variable, right? So you want to find true relationship between x and y, right? So you want to find the intercept and slope, right? Now, since it is very difficult to find, these things, right? For population, you take sample from population, right? And then you find estimates of beta 0 and beta 1, right? So basically, from sample, right, you want to find the estimates for beta 0 and beta 1, right? In this case, B0 for beta 0, right? B1 for beta 1, right? That's the basic idea here, right? Now, suppose you have data points like this, right? So you have a sample data like this, and then you mark the data points like this here. Suppose your data point looks like this, right? Now you want to find a line which is the most representative of these relationship, right? There can be many lines which go through these data points, right? For example, you can have a line like this, and you can have a line like this, or you can have line like this, right? There are other lines, right, which go through these data points, right? Among these lines, which line is the best representative of these data points? You may say that line 3 is the most representative of this relationship. Why is that? So line 3 is the most representative of these data points. It turns out that the distance, right, from each data point to line, right, you square distance from each data point to line, and you square these things. The reason that you square is that the distance can be negative, right? So by squaring these things, you make these distances positive, right? And then you add these things, right? And it turns out that line 3 minimize the sum of distance squares, right? So this means that to find the best line for representing this relationship is to find the line which minimize, right, the sum of distance squares, right? So this one is called the least square method. Right? So let me say again, right? So finding the relationship between x and y is to find a line which minimizes sum of distance squares, right? That's called the least square method, right? So let me show you how to get the slope and intercept for the regression equation, right? So now suppose that this line is the B0, B1x. Since this one is not the true, regression equation, so we are going to use y hat notation, right? Now, so let me use this one, right, to find the slope and intercept, right? So distance is the you subtract y hat, right? And then you square this thing, and you add these things, right? And you want to minimize these things, right? And since y hat is equal to d0 plus b1x, right? So you can change this one to yi minus b0 minus b1x I square, right? Now, in order to find b0, b1, which minimizes, this thing, right? Suppose this one is some kind of function, right? So what you want to do is that in mathematics, right, there is a term called partial differentiation, right? So if you differentiate the function in terms of b0 and b1 also, and you make these differentiation set to 0, right? And you have two equations here, right? And then you solve these equations, right? For b0, b1, right? So you solve these two equations for b0, b1, right? That's how we get the intercept and slope, right? I'm not going into computation part of these things, right? So this is the basic idea of getting b0, b1, right? Now let's go back to the PowerPoints. So we are back to PowerPoints. Instead of going through, the complicated computation part, right? So I'm going to show you how to get, B0, B1 by using the computer software package, right? Let's go to SPSS, and then let me show you, how to do this regression analysis, right? And then we are going to focus on the outputs, right? I already put the data. So I put x here and y here, right? And let's go to the analysis here. And we go to the regression here, right? And then you select the linear, this one, right? And you move dependent variable to the right, okay? And you move the independent variable to the right, right? And then just simply click, enter here, right? And then you get the results here, right? There are three types of tables here, right? So we are going to focus on interpreting, these results, okay? So one is for the R square value, and another one is ANOVA table, and another one is the coefficients, right? Here the 15.838, that's the intercept, and the negative 0.128, this one is the slope, right? So we are going to focus on interpreting these three tables, right? Now let me show you another one here. If you go to the regression, right, and then you choose linear. If you go to the option here, right, and you have to decide whether you want to include intercept or not, right? The default is to include the intercept, right? If you want to remove intercept, right, you remove the check sign, right? If you want to include intercept, you check this square, right? And continue and enter, right? So let me go back to the PowerPoint and then explain, these three tables, right? Now let's go to the output and then try to understand the results, right? This is the computer output. Let me explain, these things, right, one by one. And let me try to explain the R square first. Okay, this one, R square. R square is the value which shows the degree to which x explains y, right? So that means in this case it's almost 90%, right? So that means x explains 90% of y, right? And bigger R square is the better, right? And this one is simply square root of R square, okay? R square. And so that means 0.899 something, right? And this one, I'll talk about adjusted R square when we study multiple regression, right? In simple regression, it's a meaningless. So I'll talk about this one when we study multiple regression, right? And the standard error is the simply square root of this value, 0.42 something. Right? And we have 8 data points, right? So from, this table, the R square is the most important thing, right? And it, shows the degree to which x explains y, right? Now let's look at the ANOVA table. ANOVA is used to test some type of hypothesis, right? The usual hypothesis is like this. Model is not good. Right? The null hypothesis is model is not good and model is good. Right? Model is not good means, right, this one, all coefficients equal to 0, right? And this one, at least one coefficient is not equal to 0. Right? Now, for the simple regression case, right, there is only one coefficient, right? Remember that y is equal to beta 0 and beta 1x, right? This is a true regression line, right? In this case, only one coefficient, right? If you have two independent variable, in this case, we have two coefficients, right? So for the simple regression, right, the null hypothesis is just simply beta 1 is equal to 0 because we have only one coefficient, right? Now, if you have two independent variables, in that case, the for the null hypothesis, we have beta 1 is equal to beta 2 is equal to 0, right? So you write, like this, or model is not good, right? And in this case, we are dealing with the simple regression, right? So that means we use this one for null hypothesis, right? Obviously, in this case, the alternative hypothesis, beta 1 is not equal to 0, right? So the ANOVA table shows the p-value, right? Which is used for testing, this type of hypothesis, right? Now let's look at how we got, these numbers, right? And actually, this R square comes from, these numbers, right? For example, point 89 comes from 22.98 divided by 25.548750, right? So this one comes from these numbers, right? And this one is called 22.98 is called explained variation, and this one 2.56 is called unexplained variation, and 25.54 is called the total variation, right? Let's look at how we got these numbers, right? Now let's draw a graph here. So we have a regression equation like this. Okay. Now let's look at some point of x, right? And this is actual y, the observed y, right? This one is if you plug, this x number in here, and you get y hat, right? This one is y hat value, and this is y, actual y. And suppose that you don't have any data on x, right? Then what is the best predictor for y? In that case, you need to use y bar, right? So if you don't have any data on x, you have only y's, right? Then the best predictor for y is to use mean of y, that is y bar, right? Suppose this one is y bar, right? Now, this part is called the total variation, right? So y minus y bar is the total variation, right? And since we have many of these, right? And this can be either positive or negative, right? So you want to make this one as positive numbers. So you square this thing, right? And then you add this thing, right? This one is called the total variation, right? This is total variation. Now, this part, right? This part is called explained, right? So explain the variation, okay? So that means y hat minus y bar, and you square this thing and you add these things, right? This is the explained variation, right? So this one is explained variation, and this is total variation, okay? And this one, and this part is unexplained variation. So y minus y hat, you square this thing and you add, this one is called unexplained variation, right? This one is unexplained variation, right? So, and let's look at these numbers. Okay, this one is kind of variance, right? And so you need to divide these numbers by the degrees of freedom, right? So this one, 22.98, comes from dividing this by 1, right? And 0.427989 comes from dividing this 2.567934 by 6, okay? Now, how do we get these degrees of freedom? Let's look at this one first, 7. Right? Remember that we had this, right? So in this case, we have the total 8 observations, right? And then you use up 1 degrees of freedom for computing y bar, right? So you subtract 1 from 8. So that's why you get 7 here, right? Let's look at this one, 6. This one comes from here. If you look at, unexplained variation, you see here y hat. For y hat, you need to estimate the B0, B1, right? This one and this one, right? 2 things. So you use up 2 degrees of freedom. So you subtract 2 from 8, you get 6. And this one, simply, sum of this one should be equal to 7. So you have 1 here. It turns out that the degrees of freedom for regression is equal to number of independent variables, right? So if you have 2 independent variables, in that case, the degrees of freedom is equal to 2, right? And this F test statistic comes from, 22.98 divided by 0.427989, right? So this one divided by this, right? This one is test statistic, right? Remember that the F is the ratio of variances, right? And obviously, in using, this test statistic, the computer computes this, right? P-value. This one is p-value. So this p-value is less than 0.05, so you reject null hypothesis, right? As I said, this number comes from this one divided by this, right? So this is among total variation, the explained portion, right, is the R square. Okay. Now, let's look at the coefficient table. Okay. This one is intercept, and this one is the slope, right? So the regression equation looks like this. Y is equal to 15.8 something, right? Minus 0.12x, right? So that's the regression equation, right? And in this case, I'm not going into the computing, standard error, this one, but let me talk about p-values, okay? So these p-values are used for, hypothesis testing, right? Let me talk about this one first, right? Now, this is the p-value for the hypothesis testing for intercept, right? So let's say true regression is, right? So this p-value is for the hypothesis testing like this. Intercept is equal to 0, not 0. Okay? Okay? So in this case, since this p-value is less than alpha, right? So you reject null hypothesis. Okay? Now, this p-value is for the slope, right? In this case, the null hypothesis is beta 1 is equal to 0, beta 1 is not equal to 0, right? So in this case, since this one is less than alpha, right? You reject null hypothesis, right? That means what? The slope is meaningful, right? Since that's not equal to 0. So there is a relationship between x and y, right? In this case, since this one is negative, that means what? There is a negative relationship between x and y, right? Okay. So that's the interpretation of the computer output, right? Let's summarize the interpretation of this output. So first thing that you need to look at is the R square value, right? So R square value comes from the explained variation divided by total variation, right? So this one comes from that. And the ANOVA table is used for testing the overall model fitness, right? So for the simple regression, so in this case, null hypothesis is beta 1 is equal to 0. Beta 1 is not equal to 0. Since we have only one independent variable, right? If we have two independent variables, then all the coefficients are equal to 0. At least one is not equal to 0, right? So that's the hypothesis for the ANOVA table, right? In this case, this one is less than alpha, right? So you reject this null hypothesis. That means, you accept this one, right? So that means model is good, right? Since coefficient is not equal to 0, that means model is good, okay? Now, and the coefficient table you have two p-values here, right? One is for intercept and the other one is for the slope, right? So for the intercept, the null hypothesis looks like this, right? And for the slope, right? This one is same as, this one, right? For the simple regression, the hypothesis for the slope is same as the hypothesis for the ANOVA table, right? Overall model, because we have only one independent variable, right? So for the slope, p-value is less than alpha, right? So you reject null hypothesis. That means you accept alternative hypothesis. So that means coefficient is meaningful, right? So that's the main thing that you need to look at, right? So I mean the hypothesis testing, right? And if it turns out that the you accept the alternative hypothesis, right? So in this case, the slope is meaningful, right? So there is a negative relationship between x and y, right? That's it. So next time we are going to look at the multiple regression where we have more than one independent variable, right? So see you next time.